Put on your big brain, and I'm going to tell you about some game theory. It's about how designing games, especially tabletop games, is a constant struggle against solvability. It's difficult to make a game that's easy for humans to understand, and yet at the same time is so complex that even a group of humans working very hard at it can't figure out the best way to play. If they could, it would be boring, and they'd do that every time. How does that work? And what happens when it goes wrong? I will tell you. Let's start with the bad news. Any sequential two-player game with perfect information, no hidden information, and no randomness is solvable, period. All of them, all of those types of games are solvable. Now you might wonder, what if a game had randomness, or what if it had hidden information? Could that help? And also, what does it mean when I say that it's solvable? And I think we should start there. If a game is solvable in game theory terms, either it has a pure solution or a mixed solution. A pure solution is just a set of instructions that tells you exactly how to play the game. You just follow those instructions, and that's all you do. You don't make any decisions at all. And it's hardly a game at all anymore when playing the best way possible involves you making no decisions. A mixed solution in a game, on the other hand, is when you have a set of pure strategies, but there's a probability assigned to each one. Think of it like this. In a pure solution game, your set of instructions might say, if the opponent does X, then you do Y. But in a mixed solution, it might say, if the opponent does X, then 30% of the time you should do Y, and 70% of the time you should do Z. This might sound pretty similar because you're not making any decisions either when you're following these steps and just rolling dice every once in a while. But it's actually quite different. Games that have a pure solution are really worlds apart from games that have a mixed solution when it comes to the feel of actually playing them. But before I get to that, I want to answer the question I raised earlier about what if your game has some randomness, or what if it has some hidden information? Can that save us? Let's think of the kind of game that has a pure solution that I talked about, but we'll add in some randomness. Examples would be Monopoly or backgammon. You roll dice in those games, but you don't have any hidden information. Well, the bad news, and this might be a little counterintuitive, is that even though there's randomness in playing the game, you don't end up with a mixed solution. You still have a set of instructions that just tells you the best thing to do at any given moment. The difference here is that when you follow that set of instructions, you aren't guaranteed to win or draw. It would be possible to follow those instructions, to do the smartest thing at every step of the way, but then get really unlucky with your dice rolls in the game and lose. So you could follow the instructions and still lose, but if you do follow them, that's your best chance of winning. So even though the game itself has randomness, it's still a pure solution game. And what if you add hidden information? How does that affect all this? A game like poker, for example, or Pendante, which is a more fun version of poker that you can buy at surlingames.com, or YOMI that you can also buy at surlingames.com. These games have hidden information, and they are mixed solution games because they introduce the concept of bluffing. In backgammon, which is a pure solution game, you do roll dice, but you can't bluff about the result of those dice. I don't know anything more than you do about how the dice are going to be rolled in the future. But in a game like poker or YOMI, where we have a hand of cards that's private and you don't know about them, I can bluff. In other words, there is an ultimate truth to what cards I have and what cards you have and what the game state is, but I can make moves within the game to indicate that the game state is something other than it really is. You're going to have to use a mixed solution to deal with all that. Also, the card game YOMI goes even further in needing a mixed solution because it's not, strictly speaking, a sequential game. There's a double blind reveal. Both players reveal cards at the same time. So there's no way your instructions are going to say, oh, based on the game state, always do this. It's got to be a certain percentage of the time you want to block, a certain percentage of the time you want to throw. It's definitely a mixed solution game. But who cares, you're thinking? Why is a game with a mixed solution any better or really even any different than a game with a pure solution? It all comes down to one word, and that word is optimal. If you have a pure solution or a mixed solution available to you for a game and you follow it, then you are playing optimally. But what does that actually mean? There's an important difference between pure solution games and mixed solution games when you are playing optimally. With a pure solution game, there isn't really any trick to this. You just follow the instructions, you play optimally, and you win or draw if someone else is playing just as well as you. That's it. But in a mixed solution game, what playing optimally really means is not the normal English sense of the word. It's a special jargon from game theory. What it means is you're playing least exploitably. Let's use rock, paper, scissors as a simple example. Let's say you are bad at rock, paper, scissors and you play rock way too much. Someone could pick up on that tendency and they would play paper to counter you, and you would start to lose a lot of the time. So you could go back and train and decide that you don't want to be exploited anymore. You don't want people to be able to adjust what they're doing to take advantage of what you're doing. And what you would come up with is a mixed solution, which is also known as a Nash equilibrium, where what you do can't be exploited by anyone else. You would play 33% each of rock, paper, scissors. And if you do that, there's no angle someone can come in with and pick up on your tendencies and defeat them. The only thing they can really do is also play each of these at 33% to go even with you. So that's what playing optimally means. And you might be confused thinking, well, so what? This doesn't sound any better for this sort of game. But here is what it's all about. Playing optimally is not actually a smart thing to do if you want to win a tournament. Yeah, I know it's called optimal, and that is a confusing word, but bear with me. It really is not smart to play optimally. And if you think about it for a minute, that becomes obvious. To help you with the intuition, let's stick with rock, paper, scissors. Let's say you go to a rock, paper, scissors tournament, and you are going to play the mixed solution. You're the Nash equilibrium, the 33% of each of the options. You're going to do that no matter what. You're not going to make any decisions. As new information is revealed to you about how many rounds you play or who your opponents are or how good or bad they are, that has no effect on you whatsoever because you are just going to play your mixed solution. But I would not do that. That is a dumb idea. So let's imagine that one of the people you're going to go up against, and you're going to go up against all sorts of people in this tournament of different skill levels and different strategies. One of them is wearing a shirt that says, I only play paper. And he's entered several tournaments before, and he only ever played paper. In this very tournament you're in earlier rounds of the tournament, he only played paper. You are now playing him, and after your first throw, he plays paper. Okay, so what are you going to do? What are you going to do in response to this information? Well, if you want to play optimally, then you do nothing different. You just keep playing 33% of each of your options. But does that sound smart? Is that a smart thing to do? You're going to lose 33% of the time to this terrible player, worst rock, paper, scissors player in the world. And you're going to lose 33% of the time. That is a huge chance for you to lose and get knocked out of this tournament. I'm not going to lose 33% of the time to this person. I can adjust my strategy to counter them. If they're going to play paper 100% of the time, then I should shift to playing scissors 100% of the time and have no chance of losing to them. So I'm going to have a better chance of winning the tournament than you because I will be exploiting my opponent's weaknesses, whereas you won't. And so you might lose. Now, I know you might think if I play differently so that I'm trying to exploit someone, then I myself become exploitable. In this example, I was going to play scissors 100% of the time. So don't I become exploitable? Yeah, in theory, I do. In practice, though, against this player, against the 100% paper player, it's pretty easy to see that he's not counter exploiting. He's just getting wrecked. So yeah, it's possible, but you can't just automatically give up all of that advantage because you're afraid of what might happen. You need to try to exploit the opponent's weakness and see if you can get away with it. What's interesting here is that even expert players who know just about everything there is to know about a game still end up playing very non-optimally on purpose because they're trying to exploit their opponents. There are several reasons they might do this. One reason is that their opponents might be very bad, and so it becomes correct to exploit the weaknesses, even though that makes you yourself exploitable. Another reason is that most games are extremely complicated, not like rock, paper, scissors. Games like poker are extremely complicated compared to rock, paper, scissors. And something like Pendente is even orders of magnitude more complicated to solve because it has a much bigger possibility space than poker, and it has a lot more abilities and powers that you can use to maneuver your strategy. Again, you can get that at sirloingames.com. So people playing these games, even very good players who are trying to play optimally, are going to fail at it. They're often going to get pretty far off whatever least exploitable is in the various different situations that arise throughout the game. So sometimes, even with two experts, one of them might have a different and incorrect view of a very specific situation in a game, and the other is able to exploit that. And yet another angle, the most interesting angle, is when you introduce bluffs into the equation. Maybe I have powerful cards in my hand and I should play a certain way accordingly. Or maybe I have weak cards in my hand and I should play a different way accordingly. But what if I play the way that indicates I have the powerful cards? You don't know if I really have them or not. So what should you be doing? Should you be playing in a way that respects that? Or should you play very non-optimally yourself to exploit my actual weakness? That's very interesting. And this whole thing has a term that was coined by NYU professor Frank Lantz, I believe, called donkey space. So what that means is if we are both playing least exploitably, just totally by the book, then we are not in what he calls donkey space. The alternative is that I'm making moves that are very exploitable because I'm trying to exploit you, but then you see that, or you have your own tricks maybe, and you're playing in an exploitable way to try to bait me. So even though we're both very good at the game, and especially if one of us isn't, then we can end up playing a lot of this game in a space of game states, in a set of possibilities that are very non-optimal. And that's interesting. We're both doing this dance between different supposedly bad lines of play because they're exploiting each other. You shouldn't think of donkey space as some kind of edge case that's barely used. It's more like the normal state of affairs in these types of games. Again, games like YOMI or Pendente are unthinkably complicated to come up with a real, literal mixed solution for. People are going to be playing in donkey space all the time. Most players are going to be way, way off of optimal. And even the ones that are very good, they're still going to be far off of optimal too. That's before you get to all of the bluffing, which really magnifies the prevalence of donkey space. I think it's so interesting in games when you can pick up on each other's patterns. There's a lot to that, and that's what inspired me to make the card game YOMI, which is all about that. The reason I think it's so interesting is that when you're playing against someone and you're trying to pick up on their patterns and they're trying to pick up on yours, you're really having a conversation of sorts where your unconscious is speaking to their unconscious. This is the kind of thing that it seems like you should be able to consciously know about your own patterns that you're making, and you should be able to consciously pick up on theirs. Oh, I see that they're doing this certain move a lot, and so I'm going to counter it. But that is not really how it works in practice. There's some great studies on this, for example, by a researcher named Lewicki, I think in 1997 and 98. He did this study where people would look at a computer screen and there was 4 quadrants on the screen and a dot would flash in one of the 4 quadrants. And then they had 4 buttons where they had to press the corresponding button. So flash, 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 and then you press the corresponding buttons. And it was to see how fast you could do this. There was a trick to it though. It looked like that the flashes were random, but they actually secretly weren't. There was a complex set of 10 rules that governed where they would appear. So it ended up looking random, but it wasn't. And what he discovered is that as people did this, they would get better and better and better at it over time. But why were they getting better? Is the reason that they were learning the secret patterns, or was there some other reason? So to illustrate what was really going on, he then secretly switched the algorithm to make it actually random. And then suddenly everyone did way worse. And that shows, yes, they were picking up on the algorithm. So he asked the participants, do you think it's random, or do you think there is a set of rules that govern how these lights flash? And everyone thought it was random. Then he said, well, actually, it isn't random. So can you tell me what some or all of these rules are? And no one could. And then he said, what if I give you $100? Then can you tell me what any of these rules were? And no one could. And this is how extreme it was. Some of the people in this study were professors themselves in his own psychology department who were familiar with his research on this subject. And even those people claimed that they thought it was random and that there was no underlying pattern. It's all unconscious thought going on here. When you pick up on someone else's patterns, there's some deep thing in your brain that you're engaging. And again, I find that interesting. And I'll give you a bit of insight that I've learned from observing players of these kinds of games for decades, especially the card game YOMI that is really all about this. As players start to get better at this type of game, they start to realize it's all about probability ranges. I don't mean distances. I mean things like well, there's a 12% chance that I should really do this, and there's a 25% chance that I should do that. So a big part of the skill of such a game is that in a given game state, given the cards I have and you have and what's in the discard pile and which characters we are and our life totals and all sorts of other variables, given all of these things in this specific situation, what should my ranges be? And then the next step is to actually execute that in the game. Like if you decide that you should block 25% of the time, then you need some sort of mechanism that 25% of the time says you should block. So what some players tend to do is they start using randomizers, like actual dice they roll or a computer program that they get a random number from. And at first glance, I think that makes sense. But when you look closer and deeper, I find that it doesn't. The part that does make sense is that if you decide that, let's say 25% of the time you should block, and you relied on your own internal dice rolls, well, those might be imperfect and those might unconsciously have some patterns that the opponent could pick up on. In order to be more impenetrable and to not have any of those patterns, you can roll actual dice or use a computer randomizer. And I agree that that specific point is an advantage. I think there's two drawbacks though. One, which doesn't have anything to do with you winning, but it is worth pointing out, is that when you do this, I think you lose what is fun and interesting about this type of game in the first place. What's interesting is the debate that your unconscious mind can have with someone else, and you're not really doing that anymore. But the bigger point is it effective? If it is very, very effective, then it means that there wasn't really any conversation to be had anyway, that this is what everyone should be doing. But what I've found is that the players who don't do this actually end up being the better players. And I think the reason is that there's something here that cuts both ways. Step one of this was determining what your probability range should be for all the different options you have at any different time. And it changes radically over the course of a game as things happen. In YOMI, for example, you can get knocked down and that gives you severe disadvantages. So the moves that you would want to play in that situation are completely different than the moves you'd want to play in a different situation. So the first thing you have to do is figure out with what frequency you really should be playing each of your possible options in a given specific situation. And it's not going to come out to nice numbers like exactly 25%. It's going to have a million variables, and it's something that your unconscious mind is really going to have to try to solve for you. So what I've noticed is that when the very good players leverage the power of their unconscious mind to know exactly how often they should be playing all of these options, and then they sort of suffer the consequence of letting their own internal randomness do the dice roll, they end up better, even though it is a little bit exploitable there, because the alternative is that they make explicit exactly what all those probability ranges should be that they put into their randomizer program. And at that moment, right when they fix it into specific numbers they're writing down, they tend to not be really leveraging the extreme power of the unconscious mind anymore. They tend to write down probability ranges for things that just aren't as good as the ones that the best players have internalized. So at least in my experience, the players who run things almost entirely off their unconscious, impenetrable, unfathomable minds tend to do the best, which is really cool and interesting. Another relevant topic that we should think about is how pure solution games degenerate much faster than mixed solution games as players get better and better at them. Now, I've told you the difference between what a pure solution game is and a mixed solution game before, but let's think about it in a different way. Another way of saying it is that in a pure solution game, you don't have to care at all what your opponent does ever. It does not make any difference. In a mixed solution game, like the ones I've just talked about, you have to care a lot about what they do. It's a whole dance of going back and forth in donkey space and knowing their patterns and so on. Even when people know everything about such a game, they're still very interesting to play. Let's imagine players getting better at a game over time. If it's a pure solution game, like chess, for example, then at first, when no one knows anything, you don't really have any of these problems. When everyone is new to a game, no one has anything close to a pure solution. So instead, they're using their own decision-making and their own strategy, and these type of games feel really good to play. Now, I've covered that if you go to the extreme opposite end of the spectrum, where instead of everyone being new, people have the script, they have the pure solution, then there is no game anymore. There's no decisions to make. Yes, but what about steps in between? What about when we're 20% of the way there, 30%, 50%, 80%? So far, I've talked about pure solution and mixed solution in very binary terms. Either a game has a pure solution or it doesn't. Either it has a mixed solution or it doesn't. But let's think about these things as a spectrum. Let's take chess, for example, again. If chess were brand new and we were just developing strategies for it, something we would discover early on is at the end of the game, when there's only a very few pieces left on the board, that it's a lot easier to solve those specific situations. So maybe if you are left with a certain 2 or 3 pieces and I have a certain 2 or 3 pieces, we could sort of math out that there is a solution to that particular situation that now we can memorize and no longer involves any strategy. That's just a microscopic part of the game, though. That's just one situation towards the end where the pieces are a certain way. But then we would learn several more of those and we'd start to develop end game theory. We get to the point that every collection of just a few pieces of yours versus just a few pieces of mine has some sort of algorithm that you just need to learn it and know it. And if you can reach that state, you don't have to think anymore. So while you might be using interesting strategy and decisions and improvisation and so on for most of the game, in my example here, you would then stop doing that for the end game. Now, as the game developed more and more and you got more and more end games in your encyclopedia, people would also start to develop openings. There would be sequences of moves that are pretty effective at the beginning and require certain responses to not get really wrecked. So as time goes on and a game like this develops, it actually becomes more and more about memorization and less about strategy. I don't mean it becomes zero about strategy. No, because there's a spectrum here. It becomes zero about strategy at the point where it's solved. Chess, as of the time of this video, is not solved, whereas checkers is. So in chess, there is still plenty of strategy. But what I'm saying is that parts of the beginning and parts of the end game have been replaced by rote memorization and an extreme amount of memorization as well. I think chess is a great game, but I see that particular element of it as a negative. And so did some of the best players of the game. Capablanca, as well as Bobby Fischer, both lamented about how they wished that the game didn't shrink over time and how much was about improv and brilliant moves in the moment. So they really wished that something could shake the game up. Capablanca proposed one solution. Fischer proposed a different. Fischer's, he called Fischer random chess, which is now usually called chess 960, which randomizes the starting positions of both sides. Changing around the position of the pieces at the beginning of the game doesn't do anything about the end game being very calcified, but it does throw out all the opening books. There's hundreds of different initial conditions, and they'd each need their own set of opening books, and it's totally impractical. Within our lifetime, no one is ever going to develop all those opening books. So what this does is replaces a bunch of the memorization that happens in the opening with more improv strategy decision-making. So you can see what I mean about this constant struggle against solvability. There's Fischer trying to do his best against it. And I liked his idea, and I used it in a chess variant I created called Chess 2, which is a joke name. So, get over that, please. But what the game design is solving are actual real problems. I also use the chess 960 randomization of the back row, but I do a different thing that gets rid of all of the endgame memorization as well. There's something called the midline invasion rule, which I think is really fun to play with. Well, the way that works is if your king gets across the midline of the board, you win. Now, that is not easy to do, but because that exists as a possibility in the game, it immediately throws out basically every memorized endgame you'd ever have to know. You could try playing the Chess 2 variant or even the regular Chess 1 with just the change of that midline invasion rule, and I think you might find it a breath of fresh air to not have to deal with all those memorized endgames. Another example of this fight against solvability is my tabletop game, Flash Duel. Flash Duel is supposed to be a very quick and easy to play dueling game. It actually supports 1 versus 1 as well as 2 versus 2 teams and 1 versus many, where one person plays a powerful dragon. But in all these modes, and especially in the 1 versus 1 mode, it's supposed to be very fast to play. We had several tournaments for this game, several in-person tournaments. And what we found is that as players got better and better and better, the game would really drag on. It started getting incredibly long, and there was even a player who brought a graphing calculator, and that became a whole controversy. The fundamental issue that was arising is actually similar to what's going on in chess. In chess, when you have only just a very few pieces left, then it becomes actually possible to math out exactly what to do. And so you are a fool if you don't. In Flash Duel, there's a deck of numbered cards that is shared by both players. So you're both drawing from that deck. But when you get down to almost the end of that deck, then the hidden information starts to evaporate, because it means that you know the cards in your hand and you know all the cards you've discarded over the course of the game and all the cards that they've discarded over the course of the game. So as the deck itself gets closer and closer to being empty, you get closer and closer to knowing the exact contents of their hand. And so for those final few turns, when you get closer and closer to there being no hidden information, it becomes more and more possible to compute the exact, correct, perfect, pure solution to the game. When this happened, players were right to take a long time and to really start to math it all out if they're trying to win. But it was just so tedious to play and tedious to watch, and really went against the spirit of this whole game being very fast. So I revised the rules a bit and addressed this. And if you buy this game right now on sirloingames.com, you're going to be getting the new revised version of the rules. There's a few differences, and I won't go into the details. There was something called a last hits mechanic that I completely removed, but something that's very quick and easy to explain is that a change I made is the contents of the deck itself that you're drawing from, the deck with all those numbered cards. In the earlier version of the game, both players knew the exact contents of that deck before the game started. Now, they don't know the order, that's randomized, but they know what cards are in the deck. In the new version of the game, though, you actually get more cards than you need to play. And you shuffle those cards, and then you remove some of those cards, but you don't know which are removed. And then you play the rest of the game with that. So even when the deck is almost empty, there's still enough hidden information that it goes from can be computed with graphing calculator to just impossible to compute, and so no one bothers. And it made a real difference in practical play. Tournaments that we held after that point looked exactly how you'd hope they look, and they all went very fast and smooth. So in conclusion, if you're going to make a competitive strategy game, you really have to care about this whole solvability thing. And you have to understand that if you're making a pure solution game, that it's very vulnerable to more and more parts of it being replaced with just rote memorization instead of strategy. And that's something you're going to have to fight against with various things in your design. But you might consider making your game something that has a mixed solution that's more like YOMI or poker, because that sort of game doesn't really devolve into that kind of memorization as players get better and better at it. Instead, there's this really interesting skill of bluffing and dancing around donkey space that those games tend to be about. If you learned something in this video and would like me to know which part was most important, or if you have any interesting examples of all of this yourself, you can leave them in the comments below.